1.3 Complex numbers. The imaginary unit I is equal to the square root of -1, and therefore I squared is equal to -1. So that comes from squaring both sides. Note that -I is also a square root of -1. Complex numbers. If a and b are real numbers, then any number of the form a plus bi is a complex number. In the complex number a plus bi, a is the real part and b is the imaginary part. When we write answers, we're going to write them in this order, a plus bi. This is standard form. So if you write your imaginary part first and your real part after, my math lab will count that completely wrong, and on anything with partial credit, you would only get partial points for not putting it in standard form. All right, the meaning of the square root of -a. If a is greater than 0, then the square root of -a is equal to I times the square root of a. So you'll never have a negative inside the radical for a square root or an even index. It would always have an I outside the radical. So example 1, writing the square root of -a as I square roots of a. Write each number as the product of a real number and I. So example A, the square root of -16. This is the same thing as the square root of -1 times 16. So the square root of -1 is I, and the square root of 16 is 4. So the square root of -16 is 4i. B, the square root of -70 is the square root of -1 times 70. The square root of -1 is I. There are no perfect squares that I can divide 70 by, so I can't simplify that, so it's just going to be I times the square root of 70. And then C, square root of -48, -1 times. Now, if you're not sure what perfect squares you can divide 48 by, you can always use upside down division or prime factoring. So if I divide it by 2, that goes 24. 24 is also divisible by 2. That's 12. 12 is divisible by 2. That's 6. 2 times 3. So if I'm looking for square roots, I'm going to group them, whatever can be multiplied by itself twice. So I have 2 times 2 is 4. Or I can go ahead and multiply those out. 2 times 2 is 4, times 2 is 8, times 2 is 16, so 16 times 3. So the square root of -1 is I, the square root of 16 is 4, and the square root of 3 is the square root of 3. Operations on complex numbers. When working with negative radicands, use the definition the square root of -a equals I times the square root of a before using any other rules for radicands. So you always have to put it in its I form before you add, subtract, multiply, or divide your radicals. Alright, so example 2, a negative square root of -7 times the square root of -7. Before I multiply those radicals, I need to put them in I form. So this is going to be I times the square root of 7 times I square root of 7. Now I can multiply those together. So I times I is I squared. the square root of 7 times the square root of 7 is 7. Well, what do we know about I squared? I squared is equal to -1. So this is -1 times 7, which is -7. All right, example B. This is going to be I square root of 6 times I square root of 10. I times I is I squared. The square root of 6 times the square root of 10 is the square root of 60. Let's see if I can simplify the square root of 60. 2 times 30, 2 times 15, 3 times 5. So it would be 4 times 15. So I squared is -1 times 4 times 15. The square root of 4 is 2. So -2 square roots of 15. All right, C, again, we have to put this in I form. So I square root of 20 over I square root of 2. I can cancel I divided by I is still 1. So the square root of 20 over 2 is the square root of 10. You could have also just, if we, instead of going that way, if we went this way, the square root of 20 divided by the square root of 2, we could have rationalized the denominator, multiply both sides by square root of 2. So that gives us the square root of 40 over 2, 4 times 10. So the square root of 4 is 2 square roots of 10 over 2. So either way gives us the same result. All right, and then D, I square root of 48 divided by the square root of 24. I square root of 48 over 24 equals I times the square root of 2, which again, I could do it this way, or I could simplify those radicals and then rationalize the denominator and get the same result. All right, example 3, simplifying a quotient involving the square root of -a. So write -8 plus the square root of -128 over 4 in standard form a plus bi. So when we're writing in standard form, I cannot keep it all as one big fraction. So I'm going to start off by writing each over that common denominator of 4. So -8 over 4 plus the square root of -1 times 128 over 4. Let's see how I can break down the square root of 128. It's 2 times 64. So I could keep going, but right now I notice that 64 is a perfect square. So 64 times 2. So -8 divided by 4 is -2. The square root of -1 is I. The square root of 64 is 8. Oops. And then I can simplify the 8 and the 4 since they're both outside the radical. So -2 plus 2I square root of 2. To add and subtract complex numbers, you're going to add real with real and imaginary with imaginary. So to add or subtract complex numbers, add or subtract the real parts, and then add or subtract the imaginary parts. And then make sure you put it in standard form, a plus bi. So example 4, a is 3 minus 4i plus negative 2 plus 6i. So we're going to add real with real. 3 plus negative 2 is 1. Imaginary with imaginary. Negative 4i plus 6i is positive 2i. To subtract, we're going to do the same thing that I would do with polynomials. I would distribute that minus sign. So I'm going to write this as negative 4 plus 3i minus 6 plus 7i. It's important that you make sure you distribute that negative. Otherwise, you'll subtract the 6, but you won't subtract the negative 7. You'll just do minus 7i. So real with real, negative 4 minus 6 is negative 10. Imaginary with imaginary, 3i plus 7i is positive 10i. To multiply, we would multiply the same way we would binomials, by distributing or using FOIL, multiplying with the box method. The thing that you have to remember with these is that I squared is equal to negative 1. So we're never going to just leave an I squared in my answer. I squared is negative 1, so we're going to simplify it to that. So example 5a, I can multiply 2 times 3 is 6, and then 2 times 4i is 8i. And now I'm going to distribute the negative 3i. Negative 3i times 3 is negative 9i. Negative 3i times 4i is negative 12i squared. Well, remember that I squared is negative 1. So what's negative 12 times negative 1? It's positive 12. So 6 plus 12 is 18. Combine my i's. 8i minus 9i is negative 1i. B, 4 plus 3i squared. Well, what does it mean to square something? It means to multiply it by itself. So I'm going to write this as 4 plus 3i times itself, 4 plus 3i. So I can distribute the 4. 4 times 4 is 16. 4 times 3i is 12i. Distribute the 3i. 3i times 4 is 12i. 3i times 3i is 9i squared. Well, again, I squared is negative 1. So 9 times negative 1 is negative 9. So 16 and negative 9 is 7, plus, combine like terms, 24i. And then C, 6 times 6 is 36. 6 times negative 5i is negative 30i. 5i times 6 is 30i. And 5i times negative 5i is negative 25i squared. Well, we're never just going to leave an I squared because we know that I squared is negative 1. So negative 25 times negative 1 is positive 25. So combine like terms, that gives me 61. And then negative 30i plus 30i cancels. So we can write 61, or standard form to include the real and the imaginary would be 61 plus 0i. Right, the property of complex conjugates. For real numbers a and b, a plus bi times a minus bi equals a squared plus b squared. So in our last example, when we multiplied conjugates, we distributed, and then our like terms, our i's, were opposites, and so they canceled out. And then I had minus b squared, but b was negative, so minus a negative gave me a positive, so plus b squared. So the product of a complex number and its conjugate, remember, so these are conjugate, a plus bi, a minus bi. So the same terms in the binomial, but one is plus, one is minus. So the product of a complex number and its conjugate is always a real number. To find the quotient of two complex numbers in standard form, we multiply both the numerator and the denominator by the complex conjugate of the denominator. So example 6, dividing complex numbers. To find the quotient, we're going to multiply. So we basically have the same rule with i's as we do with radicals. We can't have I in the denominator. So to get rid of I in the denominator, I'm going to multiply by the conjugate. So I'm going to multiply by 5 plus I in the numerator and the denominator. All right, so you can distribute 3 times 5 is 15 plus 3I plus 10I plus 2I squared. Now don't forget that I squared is negative 1, so it's going to change that. Then on the denominator, I would have 25 plus 5I and then minus 5I, so those would cancel, minus I squared. Alright, so 2I squared is 2 times negative 1, so I can combine like terms. 15 minus 2 is 13, and then 3I plus 10I is 13I, over 25 minus negative 1, 25 plus 1 is 26. Now this is not standard form, this is not a plus bi, because I have this all together as 1. I need to separate it. So 13 over 26 plus 13I over 26. Well, those are both divisible by 13. 13 over 26 is 1/2 plus 1/2 I. On example 6, so in the denominator, I just have an I. So I don't need to multiply by a conjugate, I just need to multiply by I, because I times I is negative 1. So 3 times I, 3I. I times I is I squared. I squared is negative 1. So 3I divided by negative 1 is negative 3I. We could also write this as a plus bi, so since a is 0, it would be 0 minus 3I. Powers of I can be simplified using the facts I squared equals negative 1, and I to the 4th is equal to I squared squared. I squared is negative 1, negative 1 squared is 1. So consider the following powers of I. I to the first, well, anything to the first power is itself, so I to the first is I. I squared is negative 1. I to the third means that I have I squared times I. So I squared is negative 1. Negative 1 times I equals negative I. And then I to the 4th is I squared times I squared, which is negative 1 times negative 1, which is positive 1. Then I to the 5th would be I to the 4th times I. Well, I to the fourth we just said is 1, and 1 times I is I. I to the sixth would be I to the fifth times I. Well, I to the fifth is I. I times I is I squared, and I squared is -1. I to the seventh would be I to the sixth times another I. So I to the sixth is -1. -1 times I is -I. And I to the eighth would be I to the seventh times I. I to the seventh we just said is -I times I is -I squared. So -1 is 1. So notice a pattern. I to the first is I squared is -1, I to the third is -1, I to the fourth is I, then back to I, -1, -I, 1. So it continues to follow that pattern. I to the ninth would be I to the 10th would be -1, I to the 11th, I to the 12th, I. So powers of I cycle through the same 4 outcomes, I, -1, -I, and 1, because I to the fourth has the same multiplicative property as 1. Also, any power of I with an exponent that is a multiple of 4 has a value of 1. As with real numbers, I to the 0 is equal to 1. So simplify powers of I. Simplify each power of I. So I to the 15th. So I know that by powers of 4, every power of 4 would be equal to 1. So I can rewrite this as the closest or the highest power of 4 without going over 15 would be 12. So I to the 12th times I cubed. So I to the 12th would be the same as I to the 4th, which would be 1. And so 1 times I cubed is -1. -I. So really, you just need to memorize this pattern, and you would be able to find any power of I. All right, example B, I to the -3. Well, remember, a negative exponent gives you the reciprocal. So this is going to be 1 over I cubed is -I. I can't have I in the denominator, so I'm going to multiply denominator and numerator by I. 1 times I is I over -I squared. Well, remember, I squared is -1. So I over -1 is just I.